Consider multiplication as an analog function. Here we have two numbers on the number line, a and b, and let's look at the value of c, where c equals a times b. If a is anywhere near 1, then c will be right on top of b, wherever b happens to be. If a is greater than 1, then c will be greater than b by the same amount, no matter what the value of b is. And if a is less than 1, then c will be less than b by the same proportion. There's a symmetry to this, because if we reverse the positions of a and b, now we'll see if b is equal to 1, then c remains equal to a, whereas if b scales larger or smaller than 1, then c does the same. There's also a 0 point. When any of the factors are 0, then c goes to 0 also. And then there's the negative zone, where you have a mirror symmetry reflection about the origin, except if both numbers go negative, you'll see a and c cross at the origin, because a minus times a minus makes a plus, so the situation is not perfectly symmetrical. The scaling function of multiplication works just like an old-fashioned pantograph used to make copies of maps in the olden days. This is the way that multiplication scales value in and out from the origin. P2 is double P, and this is P3 is 3 times P, and that's the analog view of multiplication. We now know that all numbers are complex. That means they can have an imaginary component, and we can see the meaning of this in complex multiplication, where the angle of A, shown here as the blue wedge down here, and the angle of B, the red wedge, the angle from the origin to B, are added to make the angle C. See how I can make C go round like this with either A or B, because it's a rotational multiplication. It's a multiplication that goes round and round instead of in and out. Actually, this is very much what the pantograph does as well. The pantograph really works very much like complex multiplication. You can get a better idea of what complex multiplication is doing if you turn on a set of random points and multiply them all at the same time. These are all complex number points, and multiplying all by a. If a is 1, they all stay where they are. If a is greater than 1, they all move out away from the origin. If a is less than 1, they shrink in towards the origin. And if a goes negative, then they all reverse upside down and backwards through the origin. This is a very peculiar computational operation. The pantograph reveals what complex multiplication is doing. In the olden days, the pantograph was used to make copies of objects by just tracing from one to the other. And here we see the pantograph making multiplicative copies of this circle. And here we'll do a square. And you see that the pantograph is kind of pretending to be a perfect copier, an affine copier, but it does so by pivoting from a center. One could imagine a perfect affine pantograph, which would work like this, making an exact copy of objects instead of a multiplicative copy. And here we see the difference between affine spaces and vector spaces, that the affine space, every point is the same, it has no origin, but the vector space does multiplication from an origin. This is the essence of what complex multiplication is about. It's about relating the allocentric Euclidean external world to the egocentric polar coordinate system of the self-centered world. Multiplication reveals even more extraordinary properties when performing multiple multiplications all at the same time, as in linear algebra and matrix multiplication. Starting here with a standard 3x3 matrix. This one's the identity matrix. And up here we have an array of sliders that control the magnitudes of these coefficients. So I can slide these sliders here, and you see the effects on the numbers here. Now the way to visualize this 3x3 matrix is as a three-dimensional structure, and the numbers on the main diagonal here are three vectors stretching out in XYZ directions, and in the case of the identity matrix, they are all value 1. And what this matrix does is it performs a spatial transformation on any three-dimensional point in this space, multiplying its three dimensions by these three coefficients. So for instance, this here is the unit point at location 1, 1, 1, and if we multiply its XYZ coordinates by 1, 1, 1, the point remains where it started. So this is the null operation. It doesn't move points at all. If I change the X magnitude over here, you can see that that scales the point outward along the X axis. And if I make it 0, then the point loses its X coordinate. And if I go negative, it goes negative. But you can see the effect of this multiplication more clearly when you look at a whole array of clouds. Here's a point cloud, and you notice that as we scale the X magnitude in and out, the cloud stretches in and out from the center. And when we get the X magnitude to 0, it's a projection onto the YZ plane. There's an intimate connection between the concept of multiplication and projection. And of course, the same thing occurs the same way in Y, stretching in and outward from the origin, and in Z, stretching in and outward vertically. And of course, if any of these numbers go negative, the entire cloud passes through itself and makes a mirror image replica of itself across the other side. If you scale all three of the main diagonal terms at the same time, that scales the entire, all the points in and out from the origin. And of course, there's also a 0 and a negative where everything turns upside down and backwards. What about off-diagonal terms like this xy magnitude right here? This is a cross multiplication between the x and y dimensions. It shifts points in parallel to the y-axis based on their x coordinate. So the best way to visualize this is, let's make this point equal to 1, and we imagine this as a vector starting at the point x equals 1 and stretching in the y dimension, and the length of that vector is proportional to the magnitude of this coefficient. Now, in fact, a better way to visualize this is as a line, a skew line, and you can see how it multiplies points farther with larger x-coordinate more in the y direction, and ones with a lower x-coordinate less in the y dimension. For example, if we turn on this row of points, we'll see how the row of points is skewed by this skewing transformation. And there is a complementary skew, the yx skew over here, which shifts points in the x direction based on their magnitude in the y direction. So this too is best visualized as a skew line. These are skewing transformations. The determinant of a matrix also has a geometrical interpretation as the area spanned by the row vectors of the matrix, in this case 1, 0, and 0, 1. If we change these values here, we can change the area of the parallelogram, and with these off-diagonal terms we can add skew. The determinant is basically a single-valued summary of whether the matrix is generally an expanding matrix or a shrinking matrix. And it is an oriented area because if one of these terms goes negative, then the determinant goes negative. If two of them go negative, then the determinant goes back to positive again. In 3 dimensions, the determinant is the volume of the parallelepiped spanned by the row vectors of the matrix. So again, we can change these volumes, and it's again an oriented volume. There's a negative volume, and you can have skew terms here, and it goes negative again, and that brings it back to positive.